All right, let's get started. Porting privileged code applications and device drivers to x86. If you have an application that was written on Alpha or on Itanium and you're porting it to x86, there are some things that any application developer could run into. There are some more things that you could run into if you do anything with privileged code. So I'm going to take a look at like both aspects of it. And fortunately, there are some people in the audience who know some of this. So if there's are questions where I don't know the answer, I may be able to fall back on some of my colleagues. Just before we get started, when you're going to port something, an application or a driver or whatever, from Alpha or Itanium to x86, you probably want to start by looking at a few things and taking an inventory of what you have. Do you have your source code? Do you have the scripts that were used to build it on Alpha or Itanium? Do you have all the dependencies that your application relies on? Do you have a functional specification? If you do, it may make life a little bit easier if you know what the intention behind some of the code was. Are there any other design documents that you can dig up? And maybe very importantly, do you still have like a test plan that was used to test your application? If you have these, great. If you don't have them, you may be able to get by without them, or maybe you want to consider like at least writing a test plan. You need to do some planning, break what you're trying to do down in some deliverables, figure out the feasibility of porting those deliverables, assessing the risks associated with it, what could happen if something doesn't quite work the way I thought it would. Come up with estimates, how long it's going to take, come up with a testing strategy based on your test plan, and then create an overall project plan. I think this goes for pretty much any software project, and Brett wrote an article about porting software where he goes into some of these things in a little more detail. One of the things to consider if you're porting is where are you coming from? Are you coming from Alpha or are you coming from Integrity? If you're coming from Alpha, are you coming from Alpha prior to Alpha being 64-bit, or are you coming from Alpha version 7 or newer? Maybe you're coming from the VAX. Could be. And there are some resources. So we're going to produce some resources. We're going to produce a guide to porting privileged applications and device drivers to x86. We haven't released that yet. It's a work in progress, but it will cover the topics that I'm going to talk about. That's great if you're coming from Itanium, but if you're coming from Alpha, you may also want to take a look at documentation for porting applications from Alpha to Itanium. And if you're coming from VAX or from really early Alpha, you may want to look at the Alpha guide to upgrading privileged code applications, because that goes into everything you need to do to take 32-bit code and turn it into 64-bit memory-aware code. So the longer you go back, the more reading material there is available to you. So let's just dive in. Some of the things you can encounter when you're dealing with porting code is code that has been conditionalized for one or more architectures. You can find simple things like if-def alpha, or you can find if-defined VAX, or even if not defined alpha and not defined Itanium. I've come across that one. You can hope for the best and leave them like is, but like in the latter case, your x86 code will end up with the behavior that was intended for VAX. It's unlikely that that is the right decision, although there are a few places in the operating system where you could argue that the x86 behavior is somewhat VAX-like when it comes to things like alignment. We have defined __x86_64. That's the symbol that's defined if you're compiling for x86. Of course, we have the same thing in Bliss and in macro, not using this syntax, obviously, but you can do this in any type of code. I've just stuck with C for this one. The important thing is you need to think about why was this code conditionalized? And is one of these code paths the correct one for x86? Or do I need to come up with yet another way to do this that matches x86? For instance, if you want to, let me think. I'm trying to think of something that's really different across like all architectures. Well, register names. If you want to like dump some register names to the screen, and depending on the architectures, if it's alpha, it was like R1, R2. On Itanium, you had R1 and then a few more. And then on x86, you have things like RAX, RBX, RCX. So there you would clearly have to add something that is specific to x86. In most cases, you will find that the behavior that was correct for either alpha or Itanium is probably correct for x86 as well. If your code is conditionalized for Itanium to deal with the register stack engine, forget about all that. It doesn't exist on x86. The alpha code is probably right, but still verify it. There may be other places, of course, in your code where alpha and Itanium were the same and where you now have to add a conditionalization that's new for x86 because x86 does something different. For instance, if you're working in C++ and you're doing something with a size t variable, that's going to be 64 bits now. Next thing you could run into, use of assembler code. If you're running VAX, if your code is VAX macro, we can handle that. If it's system code written to deal with very VAX specific things, then maybe not. I mean, we could still handle the code, but it could be pretty meaningless. But if you have macro 64 or alpha assembly source files, or if you have IAS assembler files for Itanium, those are not going to run on x86. We can't compile them. If it's at all possible, we recommend replacing code like this with C modules. It's what we've done in a few places in the operating system. One I did was the scheduler. The scheduler is a pretty complicated bit of code, and there are 3 copies of it. There's the VAX copy written in VAX macro, there's the alpha copy written in macro 64, and there's the Itanium copy written in Itanium assembler. There is now a 4th copy, but it is written in C. Except for one module that's still written in x86 assembler that takes care of the actual context swapping that the scheduler, of course, has to do. It's a little bit tricky because when you come back from that routine, you're on a completely different stack and you may have gotten there in a different way to which you are about to leave there. That means there is some trickiness around like optimizing the C code in the scheduler. You cannot, maybe have to disable some optimizations, but if at all possible, replace it with C because it makes life so much more easier the next time you need to port. Also, just for readability and maintainability, of course. One thing to consider when you're writing assembler code is that just writing the assembly instructions isn't enough. You will also provide some unwind information so that if there is some error and the unwinder encounters your assembler routine, that you can still properly deal with exceptions. And they may be exceptions in something that you call from assembler. But if you don't provide these CFI directives to provide unwind information, the unwinder will come to your assembly routine, say, I have no way to continue from here. I'm going to call the last, like the last chance handler. That's the word I was searching for. So if you take like, this is the skeleton of an assembler routine. Go into the routine, push RBP on the stack, move RSP into RBP to establish a frame pointer, do whatever you need to do, and at the end you pop RBP from the stack again and you return. It can get more complicated than that, of course, if you need to allocate some memory on the stack, things like that. But if you have this, you really want to write this. So you want to make it a symbol that can be called probably from outside this module. You'll want to make sure that the linker and everyone else understands that this is a function. You'll want to align it at some point so you have a few like zeros before it to keep the debugger happy, that if you like are at the first instruction, it doesn't look like it's the continuation of something else. And then you have these CFI directives to say, this is where my procedure starts. This is where it ends. If you're somewhere in between here, you've ended up in land where no one has any business executing code. And you need to make sure that you have these CFA offsets and CFA registers so that the unwinder can figure out where your stack frame is, where different registers are located. And if you're lucky, these are the only directives you need to add. But if your assembler routine does more than a few instructions, it's likely that you'll have to add more of these. If there are any questions about any of this, just raise your hand while I'm talking about it, because that's easier than going back later. Otherwise, I'll just keep going. Next one, user-written threading. If you have code that does its own threading, you allocate some memory for additional stacks, and then you have some assembly routine to save the registers to the stack, switch stack pointer to your alternate stack, load registers again. You're going to have to rewrite this completely, because however you did it on Artanium or on Alpha, I can guarantee you it will look different on x86. Things to consider is, what mode are you doing this in? Are you doing this in kernel mode? Are you doing it in executive mode? Are you doing it in user mode? Could you maybe use the kernel process mechanism for this? We have something in the operating system that can do this for you in most cases. It used to be something that only worked in kernel mode, but not anymore. It works in any mode. If you're going to use that, we can help you. If not, good luck. See the calling standard. Stack frame dependencies. If you have code that goes and examines what happened before on the stack, reads directly from a normal stack frame or from an interrupt service frame or a system service entry frame, or if you have code that uses the invocation context routines and then starts looking inside the structures associated with that, looking for values of specific registers. If you're doing any of this, my guess is you're writing some kind of debugger or similar system tool. Yeah, rewrite it. Registers on all these architectures are different. How those registers are used is different. Again, good luck. See the calling standard. We have a pretty good debugger, by the way. It's getting better.
If you'd been my talk before I said this, I said the only people who ever would do this, I think, isn't the debugger.
Right.
If you're not the debugger, you probably would never do this.
If you're using C++, there are some changes. Clang is not the old DEC C++ front end. A lot of the DEC specific stuff just is not there. We can do mixed pointer sizes, but the default pointer size is 64 bits. Long size T and off T are, as on any other x86 platform, 64 bits. No longer having size T be 32 bits, even when pointer sizes are 64 bits, even though the C standard says that that's absolutely fine. You wouldn't believe how many code is written with the assumption that a pointer fits into a size T. By default, mangled names can be longer than 31 bytes. I think it's 31 characters. Yeah, 31 characters. And they can be mixed case. If you need to link your C++ code against other compilers that use shortened capitals only names, then you can use /names equals uppercase shortened.
Of course, if you're porting, you would never have names that long because you couldn't have them on previous architecture.
Right.
And
yeah.
For all things, if the C++, if you find yourself writing C++ code and you think you want to do it in inner mode, you're dead to me. I will not talk to you. Don't do that. If the first person who wants to put C++ in kernel mode, I think I'll hit them. Do not do that. I don't know where to allocate the objects.
The problem is will be that third pick up what we pick up. It's not what you want. It's what the customer did 30 years ago.
Function addresses are code addresses on x86. If you had a pointer to a function, previously it pointed to a function descriptor. That no longer exists. It now just points to code. That code may be a 32-bit addressable code stub that does nothing but jump to the real code located in S2 or P2 space. Variable length arguments list. The horribly old and outdated var args.h and associated syntax is no longer supported. Just use stdarg. Everyone else has switched over at least 20 years ago. You should too, if you're still using var args.
But if you try it, we'll see.
But not quite, right?
How about you figure out where it is?
A few specifics about if you're writing device drivers, because this is where you will likely run into some of the real changes that have happened. Buffer mapping. On Alpha and Titanium, if you want to map a buffer for a hardware device, you use something called a SVAPT, or a series of them. These are 32-bit system virtual addresses of page table entries. And then you look at the page table entry to figure out the physical address. And every single driver provides its own code to do exactly the same thing, we found. And every driver duplicates that so that it can give a physical address to the device. We have found bugs in this code. And then we found that like 3 other drivers shared the same bug. And that the other drivers did not, but 2 of them had another bug in the same bit of code. This is tricky, hairy code to get right. So for x86, well, first of all, the page tables on x86 are a bit more complex because we take 2 physical pages and map them into a single virtual page. The page table format doesn't provide for like some of the bits that we would like to see in page tables. So users manipulating them, sometimes you have 4 levels of page tables, sometimes you have 5. Getting all these bits and pieces right is tricky. We also don't have 32-bit addressable PTEs, and all these structures only provide for 32-bit addresses. So swapties are gone on x86. Any code that uses them will break. We have a new mechanism called IOBDs, IO buffer descriptors. And all of that heavy lifting of the buffer mapping, going from virtual addresses to physical addresses, is now all done by the IO exec. An IO buffer descriptor is a structure that contains a number of extents, and an extent is simply the combination of a physical address plus a number of bytes, and then you have the next extent. So this is enough to give to your device and tell it, this is where I want you to read data from or write data to. If your IO buffer is associated with a QIO, someone has asked for a QIO and it goes through the IO exec and then it comes to your driver, the IO exec is managing those buffers and it will already have filled in those IODBs into the IRP it hands to the driver. If they don't fit inside the space in the IRP, we have space for 4 IODBs in there, there will be a flag and a pointer to another buffer that then contains them. The point is, you don't even mess with those IODBs entries directly. You use calls that the IO exec provides for that. Also, if you're using your own buffers, you're responsible for managing those, but the IO exec provides routines to do that. So you don't need to touch those data structures yourself. I wouldn't touch them because maybe sometime we will have to change them. It's an internal structure. Next, page sizes. This is something you can run in if you're dealing with physical devices in a driver. OpenVMS uses 8 kilobyte memory pages. The x86 hardware provides 4 kilobyte memory pages. The way we deal with this is we treat a pair of 4K pages as a single 8K page in VMS. Now, your device may expose some IO space that's memory mapped, and the platform firmware decides where that's mapped in physical memory. And it may end up at an odd numbered 4K page. What happens if you map that page? It will be mapped in the high part of an 8K VMS page. So you will get a page address, that's the address of where it got mapped. That is the beginning of the 8K page, but the device IO space starts at an offset 4K into that page. You need to be able to handle that. If all you ever see is it getting mapped at an even size page, your code may have an implicit assumption that you can address that device IO space at the start of an 8K page, which may be true in 90% of the cases, but then you'll run it on some hypervisor or some hardware that puts it as at an odd page boundary. Just be aware that this may happen. Interrupt sharing. We find that on x86 virtual machines, there is a pretty limited number of interrupt lines available. That means that the risk that your device has to share an interrupt with other devices is higher. That means that drivers need to be able to share interrupt lines with other devices. So first of all, you need to set a bit in the driver prologue table that tells us that your driver is capable of sharing your interrupt with other devices. If multiple devices share the same interrupt and only one of those devices does not support shared interrupts, then only a single device using that interrupt will be allowed to configure. The other ones will be ignored. Well, this is how you set the bit to signal to the operating system that you can handle shared interrupts. And then, of course, you need to handle them, which means if you get an interrupt, you need to examine the device that you're the driver for to find out, has it requested an interrupt? If it has, great, you handle it and you tell us, I've handled the interrupt. If the device has not, then it means that you're sharing that interrupt with someone else, and someone else should get a chance to share it. So don't clear the interrupt bit status and tell us, it wasn't my interrupt. So we'll go to the next driver in the list that shares that interrupt and ask them, hey, can you handle this interrupt? And then finally, you may, unlikely, but if you're dealing with a device that isn't on a PCI bus, but it's like part of the old, there's no ISA bus anymore in x86 system, but the idea of an ISA bus lingers around. So you have devices that are often directly part of the CPU or the chipset that act like old-fashioned ISA devices. And some of them may use this legacy IO space that you can only access using the in and out instructions, input byte or output byte, input word, output word. And so these instructions they're funny. They're kind of like half privileged. There's a bitmap that decide which IO ports can be accessed from user mode code and which ones can only be accessed from kernel mode code. So if this bit is set, then you can do the in B and out B from user mode code. If they're not set, then you can only do it from kernel mode. Just assume you can only do it from kernel mode code. That's how we set them up by default. You could change that from kernel mode code if somehow you wanted user mode code to access these ports, but I think it's a really bad idea to do that. Just handle this inside your driver. Yeah, and I guess that's what I had to tell you. That did not take as much time as I thought it would, but I'm sure that there are questions.
A lot of times privileged code I've seen isn't doing hardware, but it's solid privilege like syslock or something, because I have a cluster aware application on my system logs. None of that has changed.
Yeah.
That goes interface perfectly fine. So it's because it's installed privilege doesn't mean you have to change anything. It might be a recompile and go. You have to
right. I think in many cases that's right. I mean, most of the mechanisms have not changed. Not many of the system service calls have changed. It's only if you do something outside of calling normal system services. If you call a system service and then start digging into some of the internal routines that are part of those invocation code context blocks. You call a system service to get them. You're not supposed to really look at them. Just use them as something you give to the next system service to do something with them. If you use one of the global symbols to find the address of some kernel data structure that is not part of the external definitions in starlet.h, those are structures that are ours. If you go messing around with the context of with the contents of those, you may run into issues going from alpha to Itanium, or going from Itanium to x86, or frankly, going from version 9.2 to version 9.3. We reserve the right to mess with those structures as much as we want to keep a working operating system. We don't go messing around with them willy-nilly. We try to, if we can, leave structures intact and only append stuff to the back of them. But when you go from one architecture to the next, the field may still be there, but it may no longer have a meaning on the new architecture.
Yeah, what Camiel is saying, the simple way of saying it is, if it's defined in lib versus starlet, then it's ours, and be careful. If it's defined in starlet, it should never change for the life of VMS. Now, that's not literally true. There's been some cases where something defined in starlet has changed, but in general, if it's in starlet, it's sacrosanct. If it's in lib, anything can happen.
Yeah, true. Not entirely true if you go from one architecture to the next, I think.
Yeah, starlet's still starlet.
Yeah, you're probably right.
Starlet.
Anything else? Yeah.
Maybe not directly related, but are the interrupts fully distributed on x86 to the different CPUs? And the second question is, does it have a meaning to define to use fastpath setting in the VM?
So fastpath in a VM. I don't think that you can pin CPUs to certain. You can pin a CPU to a physical CPU. So if you're using like fiber channel pass-through, you could like pin one of your VM CPUs to a CPU that's like physically close to the fiber channel card, and then use fastpath that way. When you're talking about like the hypervisor that provides these emulated CPUs, there's things like NUMA kind of like lose their meaning when you're in a virtual environment unless you have like really pinned things down. But you can still use fastpath to make sure that not all the interrupts happen on the same set of CPUs all the time. So it's not so much using fastpath to like tie CPUs to the CPU that's best suited for that specific device, but it's using fastpath to tie different devices to different CPUs, so you don't overwhelm one CPU with all of your IOs.
How to use performance counters in CPU?
I think so, but you'd probably have to figure that out yourself. We don't provide a mechanism to access them, as far as I know. But they are there, so there should be a way to use them.
Is there SDA extension that? I don't think.
I'm not sure. I wonder if do we use performance counters when we do like the instruction tracing? Do we use those or not? Yeah, well, PCA we're still working on for x86. That will use them. I honestly don't know.
Is the instruction you have for CPU?
Yeah.
I don't remember its name.
You can decode, we know how to code a CPU ID tree. But I just don't know if we have anything that's, we just logged on the entire performance counting tree, which is so many performance counters.
Yeah. Yeah, there are lots of them, and they differ from one CPU generation to the other.
Yes.
And once you get into like the really esoteric deep thing, performance counters that are meaningful on one generation of CPU have no meaning and therefore do not exist on another one. So I think we'd be hard pressed to find like a really generic way to expose those in a meaningful way.
And on a virtual machine, I don't know when I'm caching who's caching on.
Yeah, and I'm not even sure that all the virtual machines implement that. You may just be looking at those registers for the physical CPU, which may just have switched from a completely different virtual machine to your virtual machine. The more I think about it, the hairier it gets.
Yes.
I with them on Linux directly the driver. And never try it on the.
Right. Well, maybe try that first and see if you get meaningful numbers there.
Yeah. Yeah, they may just read as zeros. I mean, like I said, it doesn't really
Could be.
exist to start looking at some of those very specific.
Yeah.
Level 1, level 2 cache miss counters when you're in a.
Yeah. Anyone else? We can also just have a longer break. All right. Well, thank you for your attention.